All right, welcome back, everyone. Today, we're jumping right back into one of my favorite matchups in algebra, the battle for horizontal asymptotes. But this isn't just any fight. This one's a total dead heat. Now, you might remember from our last explainer, we saw what happens when the denominator's degree is bigger. It just completely overpowers the numerator and smashes the function down to an asymptote of y equals 0. Easy peasy. But what happens when the powers are perfectly matched? Who wins then?
And that's what we call the battle of degrees. Today's whole scenario is a stalemate. The degree, that highest exponent on the variable, is exactly the same on the top as it is on the bottom. It's a perfectly matched fight where neither side has that built-in advantage. So if neither one can overpower the other, how in the world do we figure out where that horizontal line is? The line the graph eventually levels off to. Well, it turns out the rule for a tie is actually surprisingly simple.
Okay, check this out. When the degrees are tied, the horizontal asymptote is just the ratio of the leading coefficients. That is it. Seriously, you just take the number out front of the highest power term on the top, and you divide it by the number out front of the highest power term on the bottom. Done.
But why? Why do only those two numbers matter? It feels a little like magic, right? But it's not. There's a really cool reason for it. And to get it, we have to imagine what happens when x gets, well, ridiculously, unimaginably huge. So let's take a look at this function here. We've got a degree 2 polynomial sitting on top of another degree 2 polynomial, a perfect tie. Now imagine plugging in like a trillion for x. That 3x squared term is going to be 3 times trillion squared. That's just a mind-bogglingly huge number. So compared to that monster, what's 7 times a trillion? Or plus 1. They're like tiny little drops of water in the Pacific Ocean. They become almost completely irrelevant. And that is the absolute key right there. As x just rockets off towards infinity, all those lesser terms, they just fade into the background. They become noise. And what's left are the most powerful, highest degree terms to duke it out. The whole function basically starts acting like it's just 3x squared divided by 5x squared. So what happens then? Well, the x squared on top and the x squared on the bottom, they just cancel each other out completely. And what are we left with? Our answer, 3/5. So the big takeaway here is that the ratio of those leading coefficients, that was the function's true destiny all along. That's where it was always headed. All right, enough with the theory. The best way to really get a feel for this is to just see it in action. So let's run through a few examples together. Okay, here's our first one. A nice, simple rational expression. We've got degree 1 polynomials on both the top and the bottom. Let's walk through it. Okay, step 1, identify the degrees. The highest power on top is 1, highest power on the bottom is 1. It's a tie. Step 2, grab those leading coefficients. We've got a 4 from the top and a 2 from the bottom. Step 3, make the ratio 4/2. And finally, step 4, simplify it. The horizontal asymptote is the line y equals 2. See? Super straightforward. All right, let's level up a little bit to some squared terms. We need to find the horizontal asymptote for this function, 3x squared minus x plus 5 all over x squared plus 4.
It's the exact same process. Don't let the extra terms fool you. First, check the degrees. Degree 2 over degree 2, yep, another tie. Now, here is a super important detail to watch for. See how the denominator just says x squared? Remember, there's always an invisible 1 in front of it. That's a classic spot to make a mistake. So, our coefficients are 3 and 1. That makes our ratio 3/1, and our horizontal asymptote is y equals 3.
Okay, one last example. This time we've got some higher powers and, yep, a negative sign, just to keep us on our toes. Don't let these bigger polynomials intimidate you. The rule is always the same. What are the degrees? Both are 3. It's a tie. What are the leading coefficients? We've got a -2 on top and a +1 on the bottom. So we form the ratio, y equals -2/1, and our final answer, the horizontal asymptote, is the line y equals -2. Simple as that. Now, this process is pretty simple, which is great, but there are two classic traps that students sometimes fall into. So let's shine a spotlight on them right now so you can sidestep them with ease. Okay, mistake number 1, and this is the most common one by far. Getting excited and just grabbing all the numbers you see. Remember, this battle is only between the leaders, the highest power terms. Those other coefficients, like the +1 and the -3 here, they're just spectators in this fight. They do not affect the horizontal asymptote. only use the leaders.
And the second pitfall is one we literally just saw in our last example, forgetting the negative sign. If that leading coefficient is negative, it absolutely, positively has to come along for the ride into your ratio. It's such a tiny detail, but if you drop it, you'll get the wrong asymptote every single time. Always, always double-check your science.
So, okay, we can find these weird invisible lines on a graph, but so what? Why does this actually matter? Does this stuff ever show up outside of a math class? Oh yeah, absolutely.
Think about a field like environmental science. Scientists use these exact kinds of rational functions to model animal populations. And in those models, that horizontal asymptote isn't just some line on a graph. It represents the carrying capacity of an ecosystem. That's the absolute maximum number of animals that the environment can sustainably support over the long haul. And here's the punchline. This is so cool. That simple little ratio of leading coefficients that we've been practicing, that's exactly what determines this critical long-term limit for a real population in the real world. That's our algebra directly impacting how we understand our entire planet.
Okay, so let's recap. We've seen what happens when the denominator's degree is bigger, it wins. Today we totally mastered what happens in a tie, which leaves us with one final fascinating question. What on earth happens when the numerator finally has the higher degree and wins the battle? Well, we're going to find that out in the next explainer.